Okay, in last video, we looked at the intuition for the limits, and today we will actually look at the idea of limits, definition of the limits, and how to solve them using different techniques. So let's imagine that we are looking at a function f of x equals to x squared minus 4 over x minus 2. Now, what happens when x is equal to 2? As you can see, we get 2 squared minus 4, 2 minus 2. We get 0 over 0, which is undefined. But here is the fascinating part. Even though the function doesn't exist at x equals to 2, we can still ask what value does f of x approach as x gets closer and closer to 2. So let me show you what I mean. Let's first factor the numerator. So we have here, let me rewrite that, f of x equals to x squared minus 4 over x minus 2. So here we have difference of squares, so that's x minus 2, x plus 2 over x minus 2. As you can see, for any x not equal to 2, we can cancel these, and we have x plus 2, which is just a line. So when x is close to 2 but not equal to 2, the function f of x is close to 2 plus 2, 4, right? So the function is close to 4. Graphically, it looks like this. We have this line here with the hole at x equals to 2 and y equals to 4, right? So we have a line here with a hole. So the function is not defined at this point, 2 comma 4, but as x moves close to this 2, our function approaches 4, and from the right side as well, we're approaching this 2. So I'm sorry, 4. So we're going closer and closer to this 4 as x approaches 2 on the x-axis, right? So this brings us to the first big definition. Intuitive definition of a limit. We write limit of f of x as x approaches some value a equals to L. If we can make f of x as close to L as we want by taking x sufficiently close to a, but not equal to a. So the key insight here, the limit doesn't care what happens at the point, only what happens near the point. So first, let's look at the tabular method for finding limits. So we have three methods. First one would be tabular, second one would be graphical, and the third one, which would be the focus of the remaining of the chapter and calculus 1 overall, would be the algebraic or analytic way of solving the limits. But let's first look at the tabular method. So let's use a table to investigate a limit. Consider g of x equals to sine of x over x. So let's find the limit as x approaches 0 of my g of x, right? So what that is. If we plug in 0 directly into the function, so when we have g of 0, it's going to be sine of 0 over 0, which makes it 0 over 0, right? This is undefined. But let's see what happens as we approach the 0. So we'll set up this small table right here. 0 is the point of interest. So I will put it in the middle, and then I will be approaching my 0 from one side and another side to see what these values are, and see if I can guess what the limit of my function is at 0. So when we have x is equal to negative 0.1, I have sine of negative 0.1 over negative 0.1. So the solution for this one will be something close to 9983. If I plug in x negative 0.01 into x, I will get sine of negative 0.01 over negative 0.01, which would be 0.9998. And if I plug in negative 0. Actually, here I'll put one more 0, so they're different. Okay. So now we're moving closer to 0, right? So it's going to be sine of negative 0.001 over negative 0.001. And the solution for this one would be, if we plug it into calculator, we get 99998. Actually, I think I missed one. Yeah, so it's gonna be this value. Now, what happens when we go from the right side? So when we plug in 0.1 into the function, so I have sine of 0.1 over 0.1. If I calculate it, it's gonna be 0.9983. If I plug in 0.01, I have sine of 0.01 over 0.001. This value is 0.99998. Okay, and here I also forgot 19. Okay, and if I plug in 0.001, I have sine of 0.001 over 0.001. The value here is 0. I think I have 6 nines. 1, 2, 3, 4, 5, 6. Like that. So as you can see, we have a pattern here, right? As x gets closer to 0 from both sides, our g of x gets closer to 1. So we can conclude from here that limit as x approaches 0 of sine of x over x is equal to 1. So this is actually one of the most important limits in calculus, so it's good to remember that. Now, sometimes a function behaves differently when we approach from the left side versus the right side. This leads us to one-sided limits. The definition is the following. Limit of f of x as x approaches a from the right side, we mark here with the plus, equals to L, meaning f of x approaches L as x approaches a from the right. This is going to be our right side limit. So values are greater than a, right? On the left side, the left sided limit would be limit of f of x as x approaches a with this negative sign, meaning that it's from left, equals to L. So we can read it as f of x approaches L as x approaches a from the left side. So values of values are smaller than or less than a, okay? Now let's look at an example. Consider h of x equals to absolute value of x over x. For x greater than 0, absolute value of x is gonna be just x, right, by the definition. So h of x is gonna be x over x, which is 1 everywhere. Now for x less than 0, absolute value of x is equal to negative x by definition, right? So h of x is going to be negative x over x, which is negative 1. Therefore, limit as x approaches 0 from the positive side, from the right side of h of x is equal to 1, and limit as x approaches 0 from the left side of this h of x equals to negative 1. So since the left and right limits are different, the limit itself doesn't exist, but we'll look at it a bit later on. So for now, let me just show you the graph, how it would look like, and we will move on. So we have this graph here. As you can see, when x is greater than 0, right? So it's this side, the right side of 0, the function is constant 1. On the left side, when x is less than 0, our function is negative 1. So it's going to be a constant like this. So it doesn't really matter if we have a definition at 0, right? Because for limits, it doesn't matter. What matters is that we are approaching, right, the values that are near that 0. And as you can see, from the left side, we're approaching -1, and from the right side, we're approaching +1. Okay, another example would be f of x equals to 2x plus 1. I want to find the limit as x approaches -1 of this f of x. So essentially, I'm looking for a limit of 2x plus 1 as x approaches -1. So using the tabular method again, I will need to create a small table and see what happens around this -1. Now, let's first look at the number line. So when we have -1 here, what are the values on the left-hand side that are close to my -1? So these values are going to be greater in the magnitude, right? But with a negative sign. So I would have -1.01, and then if I move closer to -1, I'll have -1.001, and so on and so forth, right? And from the right side, if I move closer to -1, the values right here will be smaller in the magnitude, but also with the negative sign. So this value, let's say, would be a value that is close to -1 is -0.99. And if I move closer, that's going to be -0.999, and so on and so forth. So when you're creating a table, please make sure that your values are correct, right? Because especially when you're using, evaluating the function at the negative x. So the value here would be 0.1, sorry, -1.001. And next one is -1.01. So I think 2 on the one side and 2 on the other side would be more than enough. It's -0.999. And the next one is -0.99. And when we are evaluating, it's good to start evaluating from the sides closer to the point of interest, right? So we would have here 2 times -1.01 plus 1. That is going to be -1.02. When we move closer, it's going to be 2 times -1.001 plus 1. That's going to be -1.002. And then from the other side, we have 2 times -0.99 plus 1, which is -0.98. And here would be 2 times -0.999 plus 1, which is -0.998. So as you can see, we're very, very close and moving very close to the value of -1, right? So we have -1 here. And if we evaluate, actually, we have 2 times -1 plus 1, that's going to be -1 as well. So in this case, we don't have any holes in the domain and everything is defined. So when it's defined, it's easy to use it. We will have just limit as x approaches -1 of 2x plus 1. We'll just plug in -1 here. We have 2 times -1 plus 1, which gives us -2 plus 1 is -1. So this is an easy way to find the limit in this case. Now let's look at another example where we don't have left and right limit the same. So similar to the example before, both left and right limits are not moving are not approaching the same value. So let's look at that example. So let's say we have an example f of x equals to 1 over x. And I'm interested in what happens as x approaches 0, because as you can see, if we plug in f of 0, it has 1 over 0, which is undefined. So I want to know if we have a limit or not. So again, we will set up the table, right? We have here 0 in front, and then something close to 0 would be a good idea. So negative 0.001 and positive 0.001, right? So let's check these two values, and maybe negative 0.01 and positive 0.01 would be also a good idea. So we have here 1 over negative 0.01, which is negative 100, and then 1 over negative 0.001 is going to be negative 1000. So as you can see, we're kind of approaching large negative number, right? And on the right side, we have 1 over 0.01, which is 100. And for this one, 1 over 0.001, which is 1000. Okay, so as you can see from the left side, we are approaching a big negative number, and from the right side of the 0, we are approaching a big positive number. So this one goes somewhere to negative 1000 or negative million if you move closer to 0, and this one is approaching positive. So there is a big gap between these two values, right? So that means that they're not approaching the same value as we had before with the x 2x plus 1. So we say that the limit does not exist here. Now, let's look at this example graphically, and that would be the second method that we will look at, finding limits using the graph. So the graph of 1 over x, I'll just kind of roughly sketch it, is something like this. So this is my 1 over x graph, right? So I am interested in what happens as x approaches 0 from the left side and from the right side. So as you can see, when I'm moving on the x-axis, so this is my x-axis, this is my y-axis, and I'm getting closer and closer to the 0, I see that my y value is getting further and further to the negative infinity, right? And on the right side, when I move closer and closer to my 0, again, my y values are becoming larger and larger in magnitude and going up to the positive infinity. So as you can see, limit as x approaches 0 from the left side of 1 over x is negative infinity, and limit as x approaches 0 from the right side of this 1 over x is positive infinity. So when these two numbers are or values are not the same, we say that the limit as x approaches 0 from both sides of 1 over x does not exist. Now let's look at another example where we actually have a limit, although it's not defined at that point. So let's say we have an example f of x equals to x squared plus 1 if x is not equal to 1, and 3 if x equals to 1. So this is my piecewise function. So this is my curve. So this is my x squared plus 1 approximately. And we say that when x is not equal to 1. So right here we have a hole, right? But we know that when x equals to 1, our y value equals to 3. So let me see, 1, 2, 3. So I will have a point right here. Okay? So now notice that the hole at 1 comma 2, this one 1 comma 2, and this solid point 1 comma 3. So even though f of 1 is equal to 3, as x approaches 1 from both sides, from left and right, my f of x approaches not 3, but 2. So limit as x approaches 1 of this f of x is equal to 2 and not 3, right? So we're not interested in where the function is defined. That's for the limits only. We're not interested where the function is defined. We're interested at where the function is moving or approaching to, all right, what value it's approaching from the left and right side. And if these two sides are the same, then we have a limit. Now let's look at another example where we actually don't have limit. So another example is g of x equals to 2x minus 1 if x is less than 2, x squared minus 3 if x is greater than or equal to 2. Okay, so we have a picture like this. Essentially, when x is less than 2, we have a line, right? So we're looking at this whole domain, this whole interval, and here we have our line. It starts with the y-intercept -2 and the slope of 2. So we have a line right there, like this, and it starts from the negative infinity up until this 2. And then starting from 2, we kind of break this line. We don't continue it forever. We break this line and start a new function, which is a parabola that is shifted 3 units down. So we have essentially like this, right? And we shifted down 3 units and we have something like this, but we're not interested in this piece because the parabola kicks in from x equals to 2 and on, right? So we're interested in only what starts from this x equals to 2. Actually, we can even continue that a little bit further on. Oops. So this is my parabola, x squared minus 3, and this one is 2x minus 1. Okay, so we are interested in limit as x approaches 2 from left side and limit as x approaches 2 from the right side, and see if we have if the limit exists. So from the left side, when x is smaller than 2 but approaches 2, we're looking at the linear function. So we have here limit as x approaches 2 from the left side of 2x minus 1 is gonna be 2 times 2 minus 1. That's gonna be 3, right? And on the right side, when x approaches 2 from the right side, we're looking at the parabola piece, right? So that's why we have here limit as x approaches 2 from the right side of x squared minus 3. We have 2 squared minus 3, which is 4 minus 3, that's 1. As you can see, these values are not equal to each other, and we can graphically also see that there is a gap, right? They're not approaching the same value. That means that the limit doesn't exist in this case, but we do have a left side limit and right side limit, so don't confuse those. Now this connects to the definition of two-sided limits and the relationship to one-sided limits. Okay, so the limit of f of x as x approaches a equals to L if and only if both left side limit and right side limit exist and equal to the same value or the same L. So think of it this way. For a limit to exist, the function must approach the same value from both directions, but it doesn't necessarily have to be defined at that point. It's like two friends agreeing to meet at the same spot, but if they go to different places, they don't meet. So if they don't meet, that means that the limit doesn't exist. Now, another example that I want to go over is the oscillating function when things get a bit wild. Now, something that we can discuss is f of x equals to sine of 1 over x, and we're interested in finding the limit as x approaches 0 of this f of x. So graphically, as you can see, this is the picture from Desmos. We are approaching, as we approach 0 from the left side and from the right side, our function is very kind of unstable. It oscillates a lot, right? So we don't really see if it's 0 or -1 or +1. It's hard to see. It's bouncing between this -1 and 1 and never settles on a single value. So when this happens, we say that the limit does not exist because we don't really see, we can't calculate. Even if you try to use the table and get a value that is really close to 0 from the left side, let's say something like -0.00001, or from the right side, something like 0.00001. When you calculate it, you'll see that the function is not settling at one point. So you'll see that it will be oscillating between -1 and 1 and never settling on some specific point. So in this case, we say that the limit does not exist. Okay, next time we will go over some examples and move on to the next section.